Hello everyone, my name is Tiara Devi, and this presentation I will explain chapter 10 which uh, cover the fundamentals of metal casting. In this chapter we learn what happens when molten metal is poured into a mold, how it flows, how it solidifies, and why crystal defects may occur. Understanding this fundamental is essential for producing high quality test components. Introduction. Casting is the process of pouring molten metal into a mold that has the desired shape of the final product. The success of this process mainly depends on three key aspects. 1. Fluid flow, how the molten metal moves through the jetting system. 2. Solidification, how the metal twists and forms its source through. 3. Heat transfer, how wide how heat is removed from the metal into the mold. These three factors are strongly interconnected and directly determine the final quality of casting. Solidification of pure metals. For pure metals, solidification occurs at a single temperature. As molten metal cools to its freezing point, the temperature remains constant for a while because latent heat is released during the formation of solid crystal. The temperature then drops so applied plateau during this solidification phase. At the same time, pure metals undergo volumetric change, which is one of the major causes of force. The resulting microstructure begins with fine accretion grains at the mold wall and develops into columnar grains that grow towards the center of the casting. Next, figure 10.1 illustrates the basic step involved in product casting. First, a pattern is used to create the mold CPT, which has the exact shape of the desired product. The mold is usually made of sand or another refractory material. Once the mold is completed, molten metal is poured into the mold CPT through the casting system. As the metal fills the cavity, it begins to cool and solidify from the mold walls inward. After the metal has fully solidified, the mold is opened or broken apart to remove the casting. The gating system results and any excess metal are then removed. Finally, the casting may undergo cleaning, trimming, machining, or finishing operation to achieve the required final dimension and surface curve. Next, figure 10.2 show how molten metal flows through the gating system before entering the mold CPT. The metal first enters the pouring basin which helps regulate and stabilize the flow. From there, the metal travels the wet through the screw due to gravity. At the bottom of the square, the molten metal enters the runner, which distributes the flow horizontally. The runner then feeds the metal into the mold cavity through the gate. This figure highlights how the gating system controls the direction, speed, and smoothness of the metal flow. While the designated gating system helps minimize turbulence, prevent aspiration, and ensure that the mold is followed uniformly before solidifying begins. Solidification of alloys. In alloy systems, solidification occurs differently compared to pure metal. On pure metal, with solidify at a single temperature, alloys solidify over a temperature range between the liquid and solid temperatures. As the molten alloy cools below the liquid temperature, solid crystal begin to form, but liquid still remains between them. This creates what is known as the motion zone, a region where solid and liquid coexist at the same time. During solidification, alloys typically develop dendritic structure. These dendrites grow outward into like patterns, and the remaining liquid becomes trapped between the dendrite arms. As solidification continues, these interdendritic regions may experience segregation or form microporosity if the liquid cannot flow safely through liquid the semi-solid. Because alloys have a wider freezing range, they are more susceptible to defects such as porosity and chemical segregation. The rate of cooling and the width of the Mushi-John play major roles in determining the final microstructure and mechanical properties of the casting. Overall, this section emphasizes that alloy solution is more complex than nuclear metals because of the temperature range involved, the development of boundaries, and the potential for segregation and corrosion. Next, figure 10.3 shows the temperature time curve for the pure metals and alloy during solidification. For pure metal, the temperature decreases until it reaches the freezing point. At this temperature, the metal begins to solidify and this curve becomes flat. This flat plateau indicates that the temperature remains constant while latent heat is released during solidification. Once the metal is fully solid, the temperature drops again as the solid cools. In contrast, the part for alloy slopes downward through a range of temperature instead of a flat line. Alloy solidify over a region between the liquid and solid temperatures. The region is known as the Mesin, where both liquid and solid occurs. Figure 10.4 grow out illustrates how the solid structure of an alloy grows during solidification. As the temperature drops below the liquid, solid crystals begin to form at the mouth walls. Instead of forming smooth shapes, these crystals growing in tree-like formation known as dendrites. The arms of these dendrites extend into the remaining liquid metal. As solidification consumes the space between the dendrite arms called interdendritic regions, contain liquid that gradually freeze, and if the liquid in these regions can flow out with the spin of solid, porosity of segregation may occur. This figure emphasizes the characteristic dynamic growth present in the alloy, explain during solidification, and explain why alloy often show microseparation and microporosity within the dendritic network. Figure 10.5 illustrates the detailed structure that develops during the solidification of alloys, focusing on the formation of dendrite arms and the Mesin. As the alloys begin to solidify, primary and dendrite arms grow upward from the mold walls into the liquid metal. These primary arms branch into secondary and sometimes tertiary arms, creating complex tree-like network. This structure increases the surface area between solid and liquid, which affects how it is removed and how the metal fits. The remaining liquid becomes trapped between the dendrite arms. This region called the Mesin contains both solid dendrites and liquid metal at the same time. The Mesin becomes wider when the alloy has a large freezing range. Because the liquid in the interdendritic space cannot allow for failure, several defects may occur, such as microstrains or microsegregation. Solid elements often accumulate in the remaining liquid, causing compositional variation as the alloy solidifies. Overall, figure 10.5 highlights the complex dendritic structure formed during alloy solidification and show why alloys tend to develop porosity and segregation with the Mesin. Structure property relationships. The concept of structure property relationship explains how the internal structure of metal affects its mechanical and physical properties. During solidification, the cooling rate, grain size, and microstructure features play a major role in determining the performance of the final casting. When the metal was wrapped with its own fine grain structure have more grain boundaries, which help block this cross-casing movement. As a result, the metal becomes soft, harder, and grain toward. On the other hand, slow cooling process produce coarse grains. Coarse-grained structures have fewer grain boundaries, meaning the metal is usually weaker, less tough, and more prone to deformation and stress. The direction in which grains grow also affects progress. Columnar grains which grow toward the center of the casting create directional progress. These grains can make the material strong in one direction but weaker in others. In contrast, aggressive grains provide more uniform progress throughout the casting. Segregation during solidification where element concentration in different regions can also affect progress sometimes reducing strength or causing weak spot. Overall, structure property relationship implies that the microstructure format during cooling and solidification directly determines the strength, ductility, toughness, and overall quality of the casing. By controlling cooling rate, solvent direction, and array conditions, you can design casing with their basic performance characteristics. Figure 10.6 illustrates how solidification progress in a casting and how chills and recess influence the final structure. The figure shows that solidification begins at the mouth walls, where head is extracted most rapidly. This creates a thin, solidified layer that gradually grows inward. Chills, which are highly conductivity inside placed inside or outside the mouth, accelerate heat removal in selected regions. Their purpose is to promote directional solidification by forcing certain areas to cool more quickly. As a result, the solidification process from the shelled region toward the race. The race remains liquid longer than the rest of the casting because liquid metal fits the areas that are shrinking during solidification. The racer prevents internal voids and shrinking capacities from forming. Next, figure 10.7 shows how molten metal form from the pouring basin through the gating system and into the mouth surface. The metal phase enter a pouring basin which establishes the flow and reduces turbulence from the basin. The metal flows downward through the sphere due to gravity. The sphere lets into the runner, which distributes the molten metal horizontally, and finally to the gate where the metal enters the mouth surface. The figure demonstrates how the metal level in the mouth gradually rises as the surface plus. The height of the liquid metal column above the gate determines the velocity of the flow. This velocity can be predicted using Bernoulli equations combined with friction factors as discussed earlier in the chapter. Next, fluid flow. Fluid flow describes how molten metal moves through the gating system from the pouring basin to the sphere through the runner and finally into the mouth surface. The behavior of this flow is extremely important because it determines whether the mouth will be felt soundly, and whether defects such as turbulence, aspiration, entrainment, or mouth erosion will occur. When molten metal flows, its motion is governed by the principles of fluid mechanics. One of the most important principles is Bernoulli equation, which says that the total energy of a fluid consisting of elevation heat, pressure heat, and velocity heat remains constant along a straight line except for loss due to friction. Using Bernoulli equation, we can answer how the velocity of molten metal increases as it moves from the higher level in the pouring basin to the lower point at the base of the sphere. However, the casting system are not friction as the metal moves through the sphere and runner is experiencing energy loss due to friction, turbulence, and wall roughness. This loss reduces the velocity and are influenced by introducing a friction factor and into the equation. In addition to the equation, the continuum plays an important role. It states that for incompressible fluid, the flow rate was A1 V1 sama dengan A2 V2. This means that if the flow R becomes small, such as at the gate, the velocity of the molten metals will increase. This relativity helps design screws, runners, and gates to control flow speed and prevent turbulence. Overall, fluid flow and ensure that molten metal moves steadily upward. Turbulence fills the mold completely and minimizes the effects. Proper wetting design based on these principles is essential for a secure heat-proofing casting. Fluidity of molten metal. Fluidity refers to the ability of molten metal to flow and completely fill a mold before solidification begins. It is one of the most important characteristics in casting because even if the metal has excellent mechanical properties, it cannot produce a good casting unless it can flow properly through thin sections and deflect mold features. Fluidity is influenced by several factors. First, the freezing range of the metal plays a major role. Metals with a narrow freezing range, such as pure metals or authentic alloys, generally have higher fluidity because they remain fully liquid until they reach the freezing point. Alloys with a wide freezing range tend to have lower fluidity because solidification begins early, forming a mushy zone that resists flow. The pouring temperature also affects fluidity. High or superhigh, meaning the molten metal is poured at a temperature significantly above its melting point. Improves fluidity by reducing viscosity and delaying solidification. However, excessively high temperatures can cause oxidation, gas absorption, or mold erosion, so an optimal temperature must always be selected. Mold temperature and mold material also influence fluidity. Cold or highly conductive mold express heat quickly, reducing the time the metal stay liquid and reaching fluidity. Conversely, a warmer mold allows the metal to flow further before freezing. Other factors include viscosity, surface tension, or compression, inclusion, and turbulence with the flow. Metals with low viscosity and low surface tension generally have better fluidity. To evaluate fluidity, one common test is the spiral fluidity test, in which molten metal is poured into a spiral-shaped mold. The distance the metal travels along the spiral before it reaches saturation is fluidity. The longer the spiral length, the higher the fluidity of the metal. Next, figure 10 illustrates the spiral fluidity test, which is one of the most widely used methods for measuring the fluidity of molten metal. In this test, molten metal is poured into a mold with a long spiral-shaped channel. As the metal flows through, the spiral is closely closed and evenly soaked with the design that the metal travels before it reaches saturation is fluid. A metal with a high fluidity will fill a long length of the spiral, while metal with low fluidity will rise earlier and travel only a short distance. This makes the spiral test a simple but effective way to compare the fluidity of different alloys or the influence of pouring temperature, mold temperature, and compression. Heat transfer. In metal casting, heat transfer is one of the most critical processes that determines how molten metal cools and solidifies inside the mold. When the molten metals enter the mold cavity, heat immediately begins to flow from the metal into the surrounding mold material due to the light temperature difference. This heat transfer counters the cooling rate of the metal. Faster cooling produces fine grains and strong mechanical properties, while slower cooling results in coarse grains and lower strength. The cooling rate also determines the pattern of solidification. We start at the mold walls and progress inward. The first region to form is a thin, solidified skin at the surface of the mold. The skin becomes thicker over time, following a square with reluctantly with time. The choice of mold material plays a major role in heat transfer. Metallic molds such as tissues in the casting remove heat quickly because of their high thermal conductivity. This leads to rapid solidification. In contrast, sand molds extract heat much more slowly, resulting in slower cooling and causes microstructure. Heat transfer also affects defects. Areas that cool so slowly become hotspots, which are regions that remain liquid dryness. Hotspots are particularly prone to single stability and porosity. To manage this cell may be placed inside or outside the mold to locally increase the cooling rate and promote the rectorial circulation toward the riser. Finally, circulation time can be predicted using Horner-Rule, which show that circulation depends on the volume to surface and ratio of the casting. These are Berkeley section for more solid, real green section for more quickly. Next, solidification time. Solidification time is the amount of time required for molten metals to transition completely from liquid to solid inside the mold. It is one of the most important casting parameters because it determines cooling behavior, microstructure, and the likelihood of defects such as strength and porosity. The solidification time can be expressed using Horner's rule, which says in this equation, Ts is the solidification time, V is the volume of the casting, A is the surface air drop which heat is removed, C is a mold constant that depends on mold, material and casting condition, and N is typically close to 2. This rule shows that solidification time increases with the square of the volume to surface air ratio. Casting with large volume and small surface are such as the bulky section cool and solidify much more slowly. These are become hotspots, which remain liquid the lungs and are heavily susceptible to strain defects. Conversely, casting with large surface are related to volume like than large parts cool and solidify quickly, reducing the chance of strain but increasing the risk of misrun if metal phase too early. Prof. Proof is essential for distinguish. Science risers must solidify more slowly than the casting to ensure proper feeding of liquid metal. It also helps engineer cost. Mold material determine wall thickness and design getting system that promote uniform cooling. Figure 10.10 illustrates how the thickness of a casting section affects its solidification time. In this figure, different shapes or thickness are compared to show that thicker section cool much more slowly than thinner ones. Because it may travel a longer distance to reach the mold walls, thicker section retain heat longer and remain liquid for a longer period. This figure visually reinforces Horner rules, which says that solidification time increases with the square of the volume to surface area ratio. Thicker or darkest regions have a higher if for a ratio and therefore solidifies significantly slower. Next, 10.11 demonstrates this concept of directional solidification and the importance of using research to assess ozone casting. The figure shows how solidification so highly progress from the farthest region of the mold toward the riser. As heat is exerted through the mold wall, solidification begins at the outer surface and moves inward. Proper directional solidification ensures that any strain during freezing is compensated by liquid metal flowing from the rest. The riser remains hotter and slides liquid longer than the rest of the casting. This allows it to feed liquid metal into the regions the that are freezing, preventing internal voids and screen defects. If solidification does not progress toward the rise, isolated liquid process will form and can result in screen defects. Screen cake is one of the most important defects that occurs during the solidification of metals. As molten metal cools in contact in their states, 1. Liquid contraction as temperature decreases before freezing. 2. Solidification springs as the metal transitions from liquid to solid. And 3. Solid contraction as the solid metal cools to room temperature. Because the metal volume decreases during test stage, voids can form if the screen regions are not supplied with additional molten metal. This is why lasers are used to feed liquid metal into arcs that are freezing and prevent internal CVs. Shrinkage defects typically occur in the phase regions to solidity, known as hot spots. These arcs remain liquid longer because they have a high volume to survive a ratio and less slowly. If not, feeding fat excess, shrinkage and porosity will form, reducing the mechanical integrity of the casting. Defects in casting are imperfections that form during melt filling, solidification, or cooling. These defects can reduce the performance and reliability of casting, making defect prevention a critical part of casting design and process control. Casting defects arise from various causes, including improper fluid flow, inadequate feeding gas internal and thermal stress. The main categories of casting defects include second defects, gas porosity intrusion, missions, short circuits, and mold-related defects. One second defect syndrome occurs because metal contracts at its coil and solidifies. If liquid metal cannot fit the areas that are spinning voids or cavities form, these screen defects usually occur in hot spots, regions that solidifies. Proper design and directional solidification are essential to avoid screen cavities. Next, figure 10-12 illustrates how screen cavities form during the final stage of solidification. As molten metal cools, the solidification form moves inward from the mold was towards the center of the casting. The outer region solidifies first, while the central region remains liquid once because it is insulated by the surrounding solid metal. Once the freezing form encloses the remaining liquid, a block of molten metal becomes solid at the center. Since no additional metal can flow into this isolated region, this cannot compensate for the natural volume reduction that occurs during solidification as the remaining liquid phase, void known as a screen cavity forms. Next, 10-13 show how porosity develops in alloys with a wide freezing range, unlike pure metal or electric alloys that solidify at a single temperature. These alloys solidify over a terminal interval, forming a meshy zone where solid dendrites cross with interdendrite liquid. As solidification progresses, the dendrite network becomes dense, restricting the flow of the remaining liquid metal when solidification occurs. The consequence, liquid cannot move freely to supply the screen regions instead of forming a single layer cavity. Many small, useful voids that were trapped to the mostly zone. These are known as microscreen or microporosity. Porosity is one of the most common defects that form during solidification in metal casting. It consists of small pores or cavities trapped within the metal, and it significantly affects strength, particle life, and leak thickness of the final casting. Porosity mainly forms due to lessons strains during solidification and gas entrapment. Figure 10 14 illustrates the formation of the cross-shrinkage porosity within the massy zone of an alloy during solidification. As the alloy cools, solid debris begin to grow and create a network that partially blocks the remaining liquid metal. This dendritic network restricts liquid feeding, especially in alloys with a wide freezing range. As solidification shrinks, offers the limited liquid metal in the interdendritic space cannot flow to compensate for the volume reduction. The figure shows clusters of small, irregular pores distributed throughout the massy zone rather than one large central cavity. These points, known as microstrain, reduce mechanical strength and are often difficult to detect without radiographic inspection. Next, figure 10.15 illustrates the mechanism of gas porosity formation in casting. The figure shows how dissolved gas, such as hydrogen or entered air bubbles, become trapped inside the molten metals as it begins to solidify. When the metal cools, the solidity of gas decreases sharply, forcing this out of solution. If the gas cannot escape through vents or thermally, no plus. It forms rounded or spherical pores within the casting. The figure highlights the typical appearance of gas porosity. Small round cavities often concentrated near the surface or in areas where cooling is rapid. It also shows how turbulence in the gating system can enter air into the melt, increasing the likelihood of gas process. Casting is the solidification of molten metal in a mold with metal flow controlled to Pearson defect. Solidification time depends on how surface area compression and cooling rate, will grind and dendrite structure document and properties to indicate gas and dimensional issues structuring, porosity and defects. Casting quality is an solidification, compression and trapped gas. Reference Kalpakjian S. 2010 Manufacturing Engineering and Technology 6th edition. First education is. Okay, thank you for watching and see you next video.